Let's look at problem number 10. You have a building, and the person throws the ball downward with negative 18.3 meters per second. What's its final velocity? I'm going to let you work this one out by yourselves. It's really the same answer as number 9, and I want you to think about why number 10 has the same answer as the one you just did, number 9. Tell me what you think. All right, let's look at number 11. We have a bullet that's fired straight up. It comes back down. They want to know how high it goes, so they want to know this, which is going to be y, or the change in y. Y initial is equal to 0 meters. Y final is equal to, we don't know. Acceleration, because this is free fall, is negative 9.8 meters per second squared. And our initial velocity is equal to 854 meters per second. Our final velocity. What is our final velocity right here? So right here it's going 854, and by the time it reaches here, how fast is it going? This final velocity right here is 0 meters per second. I want to know how high it goes. And what does it do when it gets to its highest point? It stops. So velocity final is equal to 0 meters per second. What formula can we use? We can use y is equal to y final squared minus y initial squared over 2a. Let me move all this up a little bit. So it's equal to 0 meters per second squared minus 854 meters per second squared all over 2 times negative 9.8 meters per second squared is equal to 37,210 meters. That's your y final, or your delta y. It means the same thing. You have to understand that nuance there. That muzzle velocity of that bullet, that's pretty high. That's about twice the speed of an average rifle. So that's a really high-speed bullet. This is something like 20 miles. So if you shoot a super bullet, it will go 37,210 meters. That's about 20 miles up without air resistance. All these problems, again and again, are without air resistance. All right, problem number 12. This is a typical drop a rock on the bird, the roadrunner, Wile E. Coyote dropping the rock on top of the roadrunner as he speeds down the road. Typical, you got some kind of object moving down the road at a constant velocity. In this case, it's 75 miles per hour. You have to do the conversion. You can't leave it in 75 miles per hour. So when I did the conversion, it was 33.5 meters per second, so it's traveling down the road. You have some object, like a tree, or in this case we have a bridge. You're going to be dropping an object out of that tree or bridge onto the moving object below. So this is really 2 problems. You have an acceleration or a free fall problem here. Here you are sitting with your bowling ball, and the bowling ball is going to be falling down, smack, right into the object as it moves by. And then once you find out the time it takes, for this bowling ball to reach the ground, you can apply that same time to how far out in front you need to drop the bowling ball to hit this particular object. So again, you just have to kind of watch and learn from this kind of problem. So what do we know? We know this y initial is equal to, we said 92 feet, which is 28 meters. Your y final is equal to 0 meters. Your acceleration is equal to negative 9.8 meters per second squared. We can use the Cliff formula. Y is equal to 1/2 at squared. Let me move this stuff out of the way here. Alright, so we don't want y, we want time, right? So we're going to have time is equal to square root of 2y over a is equal to square root of 2 times negative 28 meters, because that's how far the bowling ball falls. It falls negative 28 meters divided by negative 9.8 meters per second squared. And the time it takes for the bowling ball to reach the ground is 2.4 seconds. Okay, so this is the first part of the problem. Let me get this stuff out of the way here. So we know that we have to drop the ball. We drop the ball, the bowling ball, 2.4 seconds before the robot gets to the X mark. So we have to drop the ball when the robot is somewhere over here. That's 2.4 seconds. Now, you know that. How do you know 2.4 seconds? You can have a stopwatch and time ahead. You can't do that. So what you need to do is you need to make a line on the road before the robot gets to that position. You know that robot's coming down the road at some point. So you have like 5 minutes to do all the math. So you figure out what this distance has to be, this displacement. Displacement is equal to what? Well, how do you know how long that displacement is going to be? Again, this robot is not accelerating. This is not an acceleration problem. The reason I'm drawing this in pink now is so you understand these are two different problems. Now you know velocity is equal to distance over time, because we did this about several weeks ago. So you know that the distance that you need to drop the ball is equal to velocity times time. You have this, you have this. The velocity is 33.5 meters per second times 2.4 seconds. Seconds cancel out, you're left with meters, and you have the answer of 80.4 meters. So this needs to be 80.4 meters. So that's how far out in front you need to draw this line here. So when that robot hits that line, drop the ball. Okay, when the robot hits that line, drop the ball, and the robot and the ball will meet in the same position, smashing the robot. Saving the day, all because you know physics, thanks to TF South.